And with that, I'm now going to open the main part of class today. We're really fortunate to have a fantastic guest lecturer with us this morning. George Sowers is a professor of mechanical engineering at the Colorado School of Mines and brings over 30 years of experience in the space transportation field. He's a renowned expert on ISRU, and with his prior team at ULA, he developed an architecture for fully reusable in-space stages fueled by propellant that could be mined, refined, and distributed in space. Professor Sowers is an AIAA fellow, and we are very grateful to have some of his time this morning. Thank you, George. And with that, I will pass the baton to you.
No, great. It's nice to be here. It's great to see all the smiling faces. Before I get started, just say a little bit about Colorado School of Mines. A couple of years ago, we launched the world's first and currently only graduate program in space resources, which is a multidisciplinary program. It's we started out a couple of years ago wanting to be fully online with that program, and it is. So we were very well prepared when the lockdowns hit a year ago, and we continued on without skipping a beat, which was great. In just our third year, we're up to over 100 graduate students from 15 different countries, and I think we've got 5 continents covered now. So it's a pretty amazing program, and we're pretty excited about it. But this morning, I'm going to talk to you a little bit about a topic that's of great interest to me. So my background is, as Ariel said, is mostly space transportation. I was with Martin Marietta, then Lockheed Martin, and eventually ULA. When I retired 3 years ago from there, I was the chief scientist, and we were working on refueling architectures. And as you probably know, refueling changes everything in space. And so I'll talk to you this morning a little bit about the overall propellant economy, focusing mostly on the moon, since this is a lunar course. And I think that's where the first bang for the buck is going to come from. Little agenda, give you a very brief, one chart overview of space resources, talk about water as likely the most viable, economically viable resource in the near term, talk a little bit about water resources on the moon, some research that I've done in the last couple of years on how we would extract and process that water into propellant. And when I talk about propellant, it's liquid oxygen, liquid hydrogen primarily. Talk a little bit about the economics, because this is space mining, and it doesn't work if the money's not right. And then how we would move that propellant around into lunar space, and then some of the benefits to all the different communities that we worry about for space. So the resources in just the inner solar system are nearly infinite compared to Earth. And just a couple of examples, the power output of the sun is 10 trillion times the current power consumption of humankind. Just one large metallic asteroid like 16 Psyche that NASA is going to visit this decade, I believe, can supply all our needs for metals for millions of years at our current consumption rates. And in my opinion, if we can bring those resources within the economic sphere of humans, it will spur the next great economic revolution. You can imagine an end to scarcity. I mean, it's pretty exciting when you think about it. But for the near term, the resource that's probably most likely to be economically viable is water. And it just so happens, one of the great discoveries of planetary science in the last couple of decades is that water is all over the place in the inner solar system. It's even as far inward as Mercury, at poles of Mercury. It's very abundant on Mars, as we're finding out. Near Earth asteroids, I'll talk more about that. And we believe that there's water in reasonable quantities at the poles of the moon. For space exploration and settlement and travel, water is essential. It's essential for life. It contains oxygen for breathing air. It makes a pretty good radiation shielding. But most importantly, for the economics in the near term, we can split it into oxygen and hydrogen, and then liquefy those into liquid oxygen, liquid hydrogen propellants. We can also use water directly as propellant. There are companies working on steam-based propulsion. Bradford Space, that used to be Deep Space Industries, has a system that's actually flying. You can get low ISPs out of that. Momentous Space is working on a plasma version of a water thruster that can get you much higher ISPs. And so based on all that, I'm fond of saying water is the oil of space. It's kind of funny. I did a panel a couple of weeks ago with some environmental types, and saying that actually was a negative because some people think oil is bad. Certainly water in space is not a pollutant. The exhaust products of liquid oxygen and liquid hydrogen combustion is water itself. All right, so just one slide on near Earth objects. There's lots of them. These are objects in orbits that are similar to Earth orbit, and sometimes they cross our path. These things can be dangerous, but they also, many of them contain water in the form of hydrated minerals. And we've got some lab experiments ongoing at the Colorado School of Mines showing how you can use concentrated sunlight to break apart those minerals and release the water. Ariel mentioned NIAX. This is in support of Joel Surcell's company TransAstra, who's working on asteroid mining techniques through the NIAC program. But we're going to focus on the moon. So the evidence is starting to mount that water exists in the permanently shadowed regions near the poles of the moon. And I'm sure, as you guys are well aware, the moon has very low obliquity. That's the angle between the axis of the moon and the direction of the sun. The Earth is tilted over 20 degrees. The moon is 1.5 degrees roughly, which means at the poles of the moon, the sun is always on the horizon. And so if you have a crater or at the pole of the moon, that area never sees sunlight. It's called a permanently shadowed region, a PSR. We believe over the course of deep time, through comet impacts or asteroid impacts, volatiles have been deposited on the moon. If they're in the sunlight, they vaporize. Some of it may get swept out to space via the solar wind, but if it makes its way to these PSRs, it gets stuck. The temperatures in these PSRs is on the order of 40 to 100 Kelvin, and ice is absolutely stable in those temperatures. So if it ever gets there, it never gets out. The fact that there's ice in these PSRs has been confirmed by many remote sensing data sets. But the only real hard data point we have came from the LCROSS mission back in 2009. It was actually my Centaur upper stage. I was at ULA at the time we launched that mission. Was guided into the Cabeus crater by a small Shepard spacecraft. That spacecraft separated away from the Centaur as it was entering, and measured the spectra of the ejecta plume. And it's kind of interesting data. A very famous paper by Tony Colaprete was published in 2010. But the bottom line for our purposes is that they measured over 5% by weight water ice content. There are also a dozen or so other volatile species, including ammonia, hydrogen sulfide, other things that would be really useful for development on the lunar surface. Now, the picture on the right is neutron spectrometer data, and the purple regions are high hydrogen content, which has been interpreted to be water. But the most famous Paper recently was by Shui Lee from University of Hawaii back in 2018, where he used infrared spectrometer data to show that there's surface ice indications of up to 30 weight percent. And if you're thinking about extracting this ice, having it be on the surface is really convenient. I kind of liken it to the early gold miners that came out to Colorado. They could pick their gold nuggets, up out of the streams. Eventually when all those gold nuggets ran out, then they had to start, digging into the hillsides and blasting and doing all the hard stuff. We're at that early stage where, the first people that go mine ice on the moon are going to have an easier time of it because they can go after the surface ice. So we kind of have an idea that this resource is there. The good news is that the terrestrial resource industries are mature, and the processes for how you go from exploration results, which is where we are today, to where we want to be or need to be, which is what's called a proven reserve, is well established. There's kind of two axes here of increasing knowledge. The vertical axis is the increasing level of geological knowledge. Right now, we're pretty immature. We have remote sensing data. What we really need is ground truth data. We need to get rovers, landers into some of these deep PSRs and take samples and measurements and map and get down to where we could call it a measured reserve. And the horizontal axis are all the other factors. What's the mining technology? Can we process it into a useful material economically? Are there markets for, what we would extract and process? And then, eventually there'll be, the regulatory and government and legal and all those other factors. If you have all that put together in a package, you have what in the industry is called a proven reserve. And you can actually take that to the bank and get a loan because you've now shown that this resource exists, you understand it, and you have the technology in the markets to monetize it. So that's where we want to try and get to. So it's a combination of geology, planetary science, mining technology, processing technology, economics, and legal. It's the whole gamut. Right? It's all of that needs to come together to make this happen. The first step that has to happen is, what in the old days you'd call prospecting. Today, prospecting kind of brings an image of a guy with a mule and a pick, right? In modern terms, they call that resource exploration. In space, exploration kind of has other connotations. So, we'll try and figure out what we call this for finding the ice. But the hard part is that we got to get down into these permanently shadowed regions. There's no light down there. It's super cold. One technology that would allow us to power a rover down inside the permanently shadowed region that we've been working on at the School of Mines recently is laser power beaming. That's pretty nice because you can set your power beaming receiving station up on the crater rim, which may be close to permanent sunlight, and then beam the power. As long as you have line of sight, you can go tens of kilometers. And the areas where we think the ice is most likely to be is not really accessible by driving. Think of the bottom of the Grand Canyon, 20 kilometers from the rim. It's kind of that level of difficulty to get down into the areas where we think the ice really is in abundance. So those are some of the technology challenges you got to deal with to just go prospecting. So once we know it's there and have mapped it and characterized it, we need to extract it. One concept that I've been working on, and I actually got a NIAC grant for this, coming back to the NIAC program, is a concept we call thermal mining, which if the ice exists on the surface or in the shallow subsurface, then one way to get at it is just to heat it. And this concept, if it works, is likely to be lower cost than other methods. The brute force approach would be you dig it up, you put it in an oven, you cook it, and sublimate the ice out. In this situation, we're extracting the ice in situ without excavation. So this concept shows on the right-hand side a mirror. You can imagine large heliostats up on the rim of the crater that's concentrating sunlight onto this mirror that then redirects it through the top of a transparent capture tent, we call it. The surface is heated. The ice that's there sublimates. The vapor migrates into those little tanks you see on the sides that are cold traps. They're out in the cold where it refreezes. When those things get full, you detach them and drive them over to a processing plant where the technology is fairly straightforward to convert water into liquid oxygen, liquid hydrogen. So that's one concept. We've also thought that, if we need to get heat into the subsurface, a simple way of doing that is using conducting rods. So this is kind of the next generation of technology. It would cost more, be more complex, but we've shown in the lab that this can increase sublimation rates by 2 to 3 times. And recently we've done some proof of concept testing. The first step is creating simulants of this material. One of the big question marks is, what is this icy regolith like? Nobody knows, right? We've never been down there. We've never touched it. We've never measured it. We've never even seen it. Some people think it's, you have hard water ice cementing regolith grains together, and it's like concrete. I'm more of the opinion that it's ice grains mixed with regolith grains, because the ice has been shattered over time by impact gardening, just like the regolith has. And so we created this simulant we called the granular mix, where you take water ice, shave it, sieve it down to a certain grain size, and then dry mix it with the regolith. You got to do all that in a freezer. We purchased a walk-in freezer, and graduate students get to put their coats on and go in there and create regolith simulants. We then put that simulant in a holder, and we started out with sort of coffee cup size samples that you can see on the far left-hand side. We've now moved to larger samples that are more sort of cake sized, but chill those down using liquid nitrogen, put them in our cryogenic vacuum chamber, and then turn a little lamp on and just show what surface heating can do. And we actually showed that we could get, a decent amount of sublimation, and we could, over time, 10 to 20 hours, heat could penetrate, 5 to 10 centimeters down into the sample, which probably is enough to meet economically viable production rates for ice, depending on the actual concentrations that we have. So that's one element of a overall production system. This kind of gives you the product tree of a full propellant production system, and the color codes represent where investment has been made primarily by NASA. So in the ice extraction system, I had a NIAC. Joel Sercel has a NIAC right now, also looking at in situ. He's using microwaves in addition to just infrared. There's some mobility systems required, rovers and the like. Converting water into propellant. There's 3 different projects ongoing right now that NASA's funding. One via Paragon Space Development Corporation, that's looking at purification and electrolysis together. CSM is working with Oxyon Corporation on a tipping point award that's looking at solid oxide electrolysis. It's actually the same technology that's currently on Mars as part of the MOXIE experiment that's using electrolysis to convert Martian CO2 into oxygen for future human missions. And then Blue Origin has a tipping point award to look at the liquefaction side of it. So the good news is that, a lot of these dots are being connected. Some of the big question marks are, how do we get power down there? I'm fond of reflected sunlight if you can make it work, but that has constraints. Other people have, including me, have looked at microwave beam power. Laser beaming, power beaming is good for, maybe up to 20 or 30 kilowatts, but this production system needs megawatts. So, especially if you want to get into industrial scale. All right, so that's kind of the technology side of it. Nothing exotic, really. It's a matter of really characterizing and then just doing the system engineering development. The next side of the equation is, once I have this propellant, are there markets for it? And this is kind of where I started with this in my years at Lockheed and ULA, is the huge benefits of refueling. I spent my career trying to wrestle with the tyranny of the rocket equation, we call it, but that's the fact that the higher the delta V, as you increase delta V, the propellant mass required increases exponentially, which means the farther you go from Earth, the higher the delta V, you need giant rockets. That's why the Apollo program had the Saturn rockets. That's why NASA's creating the giant SLS. But if you can refuel, especially if you can refuel with propellants that are sourced in space, you can break that tyranny. The graph shows the blue line, which if you put realistic constraints into the rocket equation, it's even worse than exponential. It goes vertical, asymptotically vertical. But just one refueling, you can go from the blue curve down to the orange curve. And if you can refuel whenever you want, then you can basically flatten out and linearize that rocket equation. I mean, we're familiar with this from our everyday life. Imagine, you guys are in the Boston area, driving from Boston to Denver, and there were no gas stations, and all the fuel you would ever need to get to Denver and back home, you had to bring with you from the beginning. Your car wouldn't be enough. You need giant gas tanks. And then everything gets heavier, right? So your gas mileage goes down. It's a snowball effect. And now you understand why it's an exponential. You need, as you add propellant, you need more tanks. You need the propellant mass. So if you just look at the orbit mechanics, every mission beyond low Earth orbit would benefit from refueling from lunar propellant. Every single one. And I'll give you some numbers in a second. And so I imagine an eventual transition to refuelable systems, both for LOX hydrogen, for outbound upper stages, and then eventually for satellite propulsion in the geobelt, transitioning to water-based propulsion or steam. Then all of that can be sustained by a logistics stream coming up from the moon. This is a chart I've been using for many, many years. I created when I was back at ULA, but it kind of gives you the economics. So the vertical axis here is cost. The blue bars are the cost to move mass from Earth in dollars per kilogram. And you can see the physics of the rocket equation reflected in the economics of these bars. L1 is actually, from a delta V standpoint, easier to get to than geosynchronous orbit. And then you can see the lunar surface over on the right-hand side. The green bars represent the cost of mass moved from the moon, based on some business case analysis I've done. I think we can provide propellant on the surface of the moon for $500 a kilogram. And if that's the case, then lunar propellant is cheaper than Earth source propellant, even at LEO, just by a little bit. From a delta V standpoint, LEO is actually closer to the moon than it is to Earth, which is kind of an interesting fact. It just shows you the deepness and steepness of Earth's gravity well. The orange bars are kind of the bottom line. So if I can refuel with lunar propellant outbound from Earth, I can cut the cost to get to the Lunar Gateway or EML1 by a factor of 2. If I can refuel on the way from Earth to the lunar surface, I can cut the cost by a factor of 3, which I think is pretty important if you want to do anything on the lunar surface. So in my opinion, the very first thing anybody should do on the moon is to develop sources of propellant, because it makes everything that comes after it cheaper. And then if you want to come home from the surface of the moon, you can save a factor of 70, because you're filling your gas tank right there on the moon to come back. So, you know, you roll all those things into the cost of an Artemis program or any lunar development program, and you're saving billions of dollars per year. I've, over the course of the years, estimated, you know, what the total demand for LOX hydrogen propellant could be. And this is a combination of existing markets that are represented in blue. So, you know, the launch industry moves a lot of satellites from Earth into geosynchronous orbit, assuming that 3 of those would be good candidates for refueling. You know, 1 interplanetary science mission as a good candidate for refueling, 2 per year gateway logistics missions, you know, and so on and so forth. And then you get a tremendous amount of benefit from for any Mars mission by using lunar propellant. And then on the national security side, we've been talking to people about establishing a strategic propellant reserve in space. So, you know, you sum all those things up and you can, you know, put whatever uncertainty bounds on it you want. You know, you're in the, you know, 2 to 3 thousand metric tons per year of demand for this propellant. Based on all that, I've run some business case numbers, and it can work. It can work out. You know, one of the keys that has come out of this analysis is the benefit of something like a public-private partnership, and that really gets back to business risk. You know, you can imagine that terrestrial mining companies or oil and gas companies are very conservative. They don't like risk. This business, you know, especially for early adopters, will be super risky, and that's in my mind a very legitimate role for government to reduce some of these barriers of entry and risks, so that the private sector will jump. But you know, if you can bring the risk profile down to a certain threshold, then these kind of returns are, you know, especially like, you know, a 15% internal rate of return would be attractive to investors. And that's what this is showing. This is cumulative cash versus time for a mining operation. And what you'll find for any sort of aerospace endeavor, and particularly any sort of commercial lunar endeavor, you're going to have to spend a lot of money up front and go into big debt, and then hope that 10 years from then, you know, you'll start making money. But that's just going to be the fact of life. There's going to be a big front end, you know, CapEx expenditure that has to happen. All right, so those markets I showed you, most of that marketplace did not involve fueling things on the surface of the moon. It involved, refueling missions on their way up from Earth in various sorts of rendezvous orbits. I think of, use the analogy of, fighter airplanes on some kind of a mission that rendezvous with a, C-130 tanker. The tanker meets the mission where it wants to be met. And the same is going to be true for this logistics of propellant, that, if you're going from Earth to the moon, there's a certain place that's optimum to refuel. And so the idea is to set up a logistics stream that meets these missions where they want to be met with tankers. And so I envision, this sort of distribution system. We're water mining near Earth asteroids, bringing water back to an aggregation point in EML1 is my preferred location. We're mining water on the surface of the moon, moving that water and or propellant up to depot distribution centers at EML1. At EML1, we're refining that propellant and storing it. There's satellite servicing vehicles that are moving water propellant into the geobelt. And then we have liquid oxygen, liquid hydrogen propellant tankers that are meeting missions, outbound from Earth. I'm actually right now have a small STTR contract with the Air Force to investigate a logistics node at EML1. And it's kind of interesting. This is from the Air Force, not in the Space Force, not NASA. But a logistics node would have a number of critical functions. The main one would be storing liquid oxygen, liquid hydrogen propellants, and storing water. Eventually, you can imagine if there's water coming from near Earth asteroids, that you would want to process that into propellant. And so you'd have an electrolysis capability there. And then you can also have, COM. If you're in halo orbit about EML1, then you always have line of sight to Earth, and you always have line of sight to the near side of the moon. So it's kind of a convenient location. You also have direct access to pretty much any Earth orbit, which is why in a matter of days, which is why it's a lot more convenient than the halo orbits that they're looking at for the Lunar Gateway. I've talked about this already, but the basic ConOps for refueling outbound upper stages is you have a full tanker that departs the ML1 node. It enters a rendezvous orbit, and that rendezvous orbit is tailored for the mission. You would launch the payload in upper stage into the rendezvous orbit. The tanker in the upper stage would rendezvous, you transfer the propellant, and then the upper stage would do its burn to its final destination. And like I said earlier, this concept of operations lowers the cost of every mission beyond low Earth orbit. For space exploration, NASA support, again, I've already mentioned some of this, refueling logistics support missions to the Gateway, you'd get a 2x cost reduction. Refueling missions to the lunar surface is 3x. Coming back from the moon is 70x. And I've run some numbers based on some Mars architectures, and I can show a $12 billion savings per Mars mission via the use of lunar propellant, which to me is enabling. Every time NASA's been asked to come up with a cost of a Mars mission, they don't do it. The one time they did it back in, I think the days of the first George Bush presidency, it was $100 billion, something on that order. And so now they don't talk about numbers. But to me, this would be enabling for Mars missions. One that's kind of interesting and I think is more attractive to current customers is a water-based servicing of the geobelt. Today, when we launch a satellite into geosynchronous orbit, it carries all of its fuel that it will ever need at the beginning. And its end of life is determined by when it runs out of fuel. And people that are operating satellites in geosynchronous orbit manage that fuel very miserly. And every maneuver has to be carefully thought out and cost benefit analysis done. If you have unlimited refueling capability for your satellites, then you can what they call maneuver without regret, which is a phrase that's being bandied about in the Space Force these days. And you can imagine, the sort of capabilities that you can gain. You can reposition from one orbital slot to another. You can avoid and evade things. So sort of the sky's the limit in what you can do. But it basically changes the paradigm for Earth orbiting satellites. They're not one and done. You don't just launch them with a fuel load, and then when they run out, they're done. You dispose of them. The idea that you can sustain satellites in Earth orbit, not just by refueling, but by replacing parts and fixing things, is becoming the new paradigm in the world. And I had to throw this in to kind of give you an idea of the potential of lunar resources. I've talked about water and propellant as sort of the first economically viable thing, but I imagine a day when we can build large structures in space using materials sourced in space. Today when we build a spacecraft, we have to build it to survive 10 minutes of terror on a launch vehicle. We have to build it to survive 5 Gs of max acceleration and all kinds of vibration, which drives the structure, right? As you can imagine. And then our life in space in 0G is spent hauling around structure that we never need. Imagine what you can do with large space structures if you can build them in 0G. One application for large space structures is space solar power. This is a concept by John Mankins, who used to be the chief technologist at NASA, showing a 2 gigawatt power plant in Earth orbit. Geosynchronous orbit is the place people like to put them. It's enormous. It's 13 kilometers by 6 kilometers. And it would be 10,000 metric tons if launched from Earth, which is, way more, I haven't looked at the numbers, but it's, way more than the mass of everything ever launched. But, and I've looked at these numbers as well, if you can source the materials on the moon, assemble this thing in L1, then you can close a business case. And I've run numbers, on the order of $10 billion for this power plant, which is very comparable to, like a new technology nuclear power plant. But the benefit of space solar power is that it's inexhaustible. Unlike solar energy on Earth, it works at night. It's not susceptible to having your solar panels covered by snow, which is what happened in Texas a few months ago. So it's impervious to weather, inexhaustible power available 24/7. So it's a good candidate for baseload power, which, current renewables are not. Wind and solar are intermittent. So they're, even if no matter how much wind and solar capacity you put in, you still have to have, fossil fuels for baseload or nuclear for baseload. So, this is one of the opportunities that could be imagined via the use of lunar resources that could really change the way humans live on Earth and solve some of our current problems. So with that, I'm kind of done. I got one last quote, and This is by John Marburger, who was the presidential science advisor for the second George Bush. And he made a speech, and I was actually in the audience, and it made a big impression on me. The moon has unique significance for all space applications for a reason that, to my amazement, is hardly ever discussed in popular accounts of space policy. The moon is the closest source of material that lies far up Earth's gravity well. Anything that can be made from lunar material that costs comparable to Earth manufacture has an enormous overall cost advantage compared with objects lifted from Earth's surface. The greatest value of the moon lies neither in science nor in exploration, but in its material. All right, and so that I'm done, and I saved about 15 minutes for questions.
Thank you, George. Fantastic presentation on several different aspects of ISRU, the economic case, growth potential from this, getting several claps from the team here over Zoom. Thank you. Any questions? I'll open it up to the class directly.
Yeah, hi, I have a question. So I have two questions, sorry. Yeah, the first is there comparison about the quantity of the surface water and the subsurface water? Is there a comparison which is more? A second question is from the image you showed to determine the position of the water ice reserve, how to decide where the water ice reserve is just by a single point measurement? Thank you.
Yeah, so the answer to the first question is nobody knows. And like I said, we've never been to these areas where we believe the ice exists. There's never been a lander in one of these PSRs. There's never been a rover in one of these PSRs. All we have is remote sensing data. And that one data point I showed where we smashed the upper stage into the Cabeus crater. I will say that one of my colleagues here at the School of Mines, Kevin Cannon, has done some pretty interesting analysis looking at the formation and evolution of ice on the moon, assuming that in deep past it started out as a surface layer, and then came up with some analysis on how it would be gardened in by impacts. And that analysis showed that most of the ice is within the first meter. But the direct answer to your question is nobody knows, and we need to go and find out. The second question is, it depends on the answer to the first, right? We've done some estimates and various people have done estimates based on a lot of assumptions and some of that remote sensing data, that there's, on the order of 10 billion tons of ice per pole. But, the error bounds on that, estimate are enormous. So we don't know. We don't know how much there is really there. And that's the first thing that needs to happen. Talk to your NASA representatives. We need to go and find out. They have a mission called Viper that's planned for a few years from now. But the problem with Viper, and I don't want to sound too negative here, is that it's going to a shallow PSR that you can drive into and drive out of, because that's all it can do. And unfortunately, the data suggests that the ice is in the deep, the really deep, large PSRs, not necessarily in the shallow ones. So my fear is that Viper goes and pokes around in a shallow PSR and doesn't find anything, and then the headline is there's no ice on the moon.
So, sorry, another quick question. Will the water ice deposition change over time? I mean, the position would change over time?
Not much. It's pretty ancient stuff. It changes, when it gets impactors hit, right? Some of it gets ejected and churned around a little bit. Some of it will actually leave. and get swept out by the solar wind. There's speculation about, longer term deposition processes. There's solar wind implantation that creates small amounts of water, things of that nature. So, there's a continuous sort of water cycle evolution on the moon that's poorly understood right now.
Thank you.
You want me to call on people, or?
If I could pop in with a question, actually, Professor. I think you had one slide going over the cost comparison of resources from Earth's surface compared to lunar resources, but I was wondering if you could go into more detail and potentially how an orbital like refueling and servicing business case delivering resources from Earth's surface may compare with one dependent upon lunar resources, and whether, in your opinion, maybe that could be sort of a stepping stone to develop some of the technology.
Yeah, no, you're right. That is a stepping stone. In fact, I first got into the thinking about refueling with a concept called distributed lift, where we launch a tanker from Earth and refuel. And that's actually quite beneficial as well. It's not as, it depends on where you're going, but it has the effect of just like staging does. So if you do that technique, then you definitely get benefit relative to not doing it. So that's good, and you can start doing it that way. And we actually proposed when I was at ULA doing missions exactly that way. And not to air dirty laundry, but we were told to stop. If you can refuel, and the reason being, if you can refuel, then you don't need as larger rockets. And there's some people that are going to make a lot of money by building large rockets. So yes, the answer is yes. That's an excellent technique to do, and I think things will start that way. So, a couple of people have their hands up. Colin.
Thanks, sir. As a Space Force officer, it's nice to hear you drop the name a few times when talking about cislunar and lunar, because it's not talked about enough. I have a quick question on an overall grand cislunar strategy. So space nerds tend to get pretty myopic in their interest when they start talking about space, right? For example, the debate over a LOX tug versus a nuclear tug is very heated and tends to take away from the overall benefits of a tug in general. And they're all working, for similar interests, right, without working together. How many of our problems do you think could be solved with just a whole of government cislunar/lunar strategy along the lines of not only the strategic technologies that you talked about, but climate change, exploration, military, and how all those kinds of things work together? Is there much research overall on the overall cost for a kind of whole of government strategy?
So I don't think, I think it kind of started under the last administration with the creation of the Space Council, which was, I think, a great move. And I was super pleased to see that the current administration kept it going. That it's a perfect thing for those guys. I mean, Scott Pace, who was the director of the Space Council under the Trump administration, was beginning those discussions. And you could see that in some of the space policy directives that came out. You could see that just with the foresight in creating the Space Force, which is something that those of us in the business have been, advocating for decades. But yeah, I think there's room for a lot more of that discussion. I will tell you the variant of the briefing I just gave you guys, I gave to the Space Force Chief Scientist's office back in January. So those guys are thinking about it. It's evident by the fact that, this logistics center that we're talking about, that I showed a picture of, is the subject of a STTR grant from the Air Force. So they're starting to get into it more and more. But I think what you just suggested is a great idea, and talk to your congressman. I don't know. Be great to get a whole of government, consistent approach. All right, DD, that's all I can see on the screen.
Oh, yes. Hello. Thank you. Amazing presentation. My question is simple, but is it possible to harvest energy from the craters using the difference of temperature, that really huge drop in temperature from the surface to the crater, and then probably use that energy to melt the ice in combination of other techniques like the elegant solution that you presented as reflectors?
Yeah, I don't know. The kind of the fun thing about this is that we're at the very beginning. Nobody's actually done any of it. So right now there's a number of competing ideas. So you're thinking of heat pipes or something like that?
Like thermoelectric energy harvesting, where you have a difference between, two probes that give you a potential, and then use that energy to harvest, and then maybe shoot a laser like you suggested, or use that energy transfer in a third electrode to heat the center of the crater.
Yeah, no, I don't know. It's not something I've thought of. Sounds like a great NIAC proposal. But yeah, one of the challenges is that the distances from where we think the ice really is, and you have to think back to that picture, and maybe I can show it again. This it's now famous picture by Shui Li. You can see, and look at the right-hand one, the South Pole. Like there's sort of these three craters in a row. That one in the middle is Shoemaker. It's 50 kilometers in diameter. And so the distance from these areas of permanent light, which are kind of on the rims, to where those ice indications are most dense, is probably 10 to 20 kilometers. And so that's what you're dealing with. So there's a large distance between where the energy can be collected and where you need to get it to. The downside of the reflected sunlight is it probably has a max range of maybe 5 kilometers. Maybe you can push it up to 10. That's why I think microwave power beaming might be the ultimate answer, because that could be effective easily at 20-30 kilometers. So you can imagine the power grid on the moon is a bunch of solar collectors near the South Pole or the North Pole, and beaming power all around the landscape.
Thank you.
All right, so are we done?
We have one more question, George, if you're open to it. Vaishi?
Yep.
Hi, this is Vaishi. Thank you again. This was a really, really wonderful presentation, and comprehensive as well too. So I'm on a team with Fangzhen, and one of the ideas that we've been throwing around has been to look at changes in the atmosphere or the exosphere of the moon, maybe as an indicator, with using a wireless sensor network. And I wanted to get your thoughts on that. So for example, having a miniature spectrometer in order to study the atmosphere, maybe looking at evolution from these impact events, or from the whole water cycle as you talked about. Is that harebrained? Is anybody doing anything like that? Just what
I'm not personally aware of people doing stuff like that. I freely admit I'm not a planetary scientist by trade. I was educated as a physicist, and then was a rocket guy for most of my career. Now I'm in ISRU, but I think there's a lot that can be done in studying this water cycle. My fear is that the time constant on this water cycle is, way longer than human lifespans. And we're talking about really slow processes that have acted over billions of years. I think the consensus is most of the ice is ancient and probably came from that early bombardment period in the solar system, and has just been there because it's too cold in the PSRs to ever sublimate. And there are thoughts that impact events does liberate chemically bound water and some of the minerals in the mares, for example, have some water content. It's low in the parts per million, and that has continuous processes, and the solar wind is implanted, planting hydrogen atoms that could become bound with oxygen that's in the regolith to form water. But those are really slow processes. So, what you're talking about might work, but the processes might be so faint that you can't see anything.
But it could be that all you need is just a threshold in terms of an indicator of where to land, to where to bring in a more, we're thinking of it as a course search.
Mm-hmm. Yeah,
Thank you.
Sounds interesting.
Fantastic. Well, George, thank you so much again for spending a whole hour with us this morning. We really appreciate the fantastic talk and the engagement with the questions. If they'd like to make any other comments before we close that, I think we'll give the students now a break between the two halves of the class.
No, I wish you all luck. I mean, one of the reasons why I went from industry into academia as a sort of twilight of my career is to encourage you folks to go do this. So I'm happy that you're interested, and I think it's a really exciting time to be getting into this field. I think finally we're going to go back to the moon, and there's enough commercial interest that will go back to stay.
I agree, and I'm very hopeful that we are at this inflection point again, and it'll be, as we say at MIT, our mission to the moon to stay. So thank you again.
All right.
The class can just please join me in thanking George. Thank you very much.
Thanks.